Okay, so if you were to make a quick analysis of, say, this particular truth table, only this one, okay, let's say A and B. So A says call it, I mean, it can be anything, but for our purpose, since they're both inputs, we're going to call them switch. Let's pretend that they're both switches. So B is switch number 2. And Y is, let's say, a light bulb. So light, and it's an output. Okay, so examining scenario number 1, we can see that when switch 1 is off and switch 2 is off, then the light is off, which makes a lot of sense. Both switches are off, the output is off. Scenario number 2 is saying that when switch number 1 is off and switch number 2 is on, then the output is off again. So this seems to be that switch number 2 does not control the output directly. Let's move on to scenario number 3. Scenario number 3 is saying that when switch number 1 is on, switch number 2 is off, the output is off again. Finally, scenario number 4 is saying that only when both switches are on can the output be on. So we can conclude from that truth table that only when both input A and B are 1 can output Y be 1. Or we could also make notes to ourselves that the scenario that we're talking, we're going to say that, hey, there are 2 switches, and only when both switches are on can the light turn on. So first, over here, I have a problem. Let's say our employer has given us a problem to solve. It's called the flashing indicator light. And it is saying that when input I 0.1 is true or 1, then output Q 1.1 flashes at frequency of 0.5 hertz. Okay, so one thing I'm going to make clear quickly is that I is short for input, and this is by convention written that way. Then the number coming after it, so we can see 0.1, 0.2, 0, is the location of the memory of where it is located at, and its bit. We are not going to get into that. And it goes from 0 to 7. So for example, over here we have 0.0, and that cannot go up to 0.7. And if you're going to bring in more input, then it would go on into 1.0 to 1.7. And today we're going to be focusing more on truth tables. So if I were to explain bits and bytes, then the video will be too long. I really strongly suggest you go ahead and have a read for yourself on this topic. Anyway, the number points to the location of the input. And finally, we have the state, which is 1, which we talked about already. Then another thing we need to be familiarized with is Q, convention for output. So it's referring to output, and then again, the same thing. It's 1.1, the location. And furthermore, it is talking, it is specifying what it is. So it seems to be that it's a light. It's a blinking light, to be specific, that flashes at 0.5 hertz frequency. Okay, so that's clear. Okay, so and from the first sentence, all we need to deduce is that the input, we can call it switch. So switch 1 controls output 1.1 or light 0.5 hertz. We can name it that. Statement number 2 says that when input 0.2 equals 1, input 0.2 is another input. So We know that it's another input because the location of it is different. We can even call it like perhaps input 2 or switch number 2. We can call it by the location number. We can name it like that. That's how I go usually. So this controls output 1.2, which seems to be another flashing light, which blinks at a different frequency. This happens to be 1 Hertz in this problem. And the final sentence is saying that when the input 0.0, so another input, perhaps another switch. So if this is switch number 1, switch number 2, so switch number 3 is on, both outputs, so input 0.0 seems to be controlling both of the lights. So output 1.1 and 1.2 are in zero state. So all sentence number 3 is saying is that when I 0.0 is on, no Q can be 1. So none of the lights can be on if switch number 3 is on, regardless of if switch number 1 or 2 are on. So both switches can be on, but as long as the main switch, we can call 0.0 the main switch. As long as the main switch is on, it does not allow either of those outputs to be on. So how do we make a system like this? I guess this is quite simple. You can just think about it logically, but it can get complicated really fast. Let's say, for example, if we have, 20 switches, 30 outputs, and let's say 5 main switches. Then what are you going to do? It's perhaps if you're very smart, you could think about it, but it's not very wise. It's going to take a very long time, and mistakes are bound to happen that way. So that's why we have truth tables. Okay, so over here, I have pasted a picture of the problem that we just analyzed. And over here, I'm going to attempt to make a truth table. Before I start the truth table, I'm just going to quickly explain one thing that I'm going to be doing. So what we really need to realize is that the scenarios inside the truth table are dependent on the amount of inputs. So this is the general formula you go by. So 2 to the power of n. So 2 to the power of some number, and that some number n equals I. Okay, what is I? I, we established already that it's the input. So a number of inputs. For example, if we have 4 inputs, then 2 to the power of 4 would give us 16. So 16 arguments inside the truth table. And don't worry, I will explain this very quickly in just a. And don't worry, I will explain this very quickly. In our scenario, so in our problem, we are given 3 inputs, right? I 0.1, I 0.2, and I 0.0. So that's 3 inputs. So how many scenarios should the truth table give us? Well, if you said 2 to the power of 3 equaling 8, then you're correct. So now let's create the truth table and explain what are these scenarios that I keep mentioning. We're using Excel because Excel provides a very nice platform for truth table, very organized. You don't have to use it if you don't want to, but I would like to use it. But if you do it correctly, the end results should be the same. So how would we go on about creating it is that let's put input over here. So over here, these will be our inputs. So how many inputs do we have? We have I 0.1. So that's the so-called first switch. I can maybe put in parentheses the switch 1. So the first switch that controls the first light. Then we have input 0.2, which is, we can call switch number 2. And finally, we have switch 0.0, which was the overpowered switch. Let's call it the main switch. So this one actually controls both of the outputs. Well, not directly, but partially. We'll get on. We'll talk more about that. So then, furthermore, from the question, we can see that we have two outputs. So if I just write maybe outputs like this, and let's write the first output, so Q 1.1, and then Q was it 1.2? Yeah, Q 1.2, and these are our only two outputs. Perfect. So now we can put the question away. And okay, so truth table, we established that we need 8 arguments. I'm just going to put it near an input so that we remember. So 8 arguments. And what does this 8 mean? So when you have 8 arguments, that means that you need to have 8 rows. Each argument occupies 1 row on the Excel sheet. So each argument, 1 row. So we need to have 8. So we need to fill it up until 9. Okay, and how would we go on about it? You just need to do this, and trust me, you will see why. And for now, just trust me and do it. So you start with 0. It doesn't matter if you start from left or right, from the first input or from the last input. What really matters is that you're consistent. So if you're starting from right to left, then just go input by input. For example, if I start from input 0.0, I cannot just jump to input 0.1. I have to next do input 0.2. Okay, so we go 0, 1, 0, 1, 0, 1, 0, 1, and that's it. And the one thing to really look out for is that you start with a 0 and you must end with a 1. So you start with a 0, you end with a 1. And now we must go to input 0.2. We cannot go to input 0.1 because that's going to mess up our truth table. All right, the next one goes 0, 0, 1, 1, 0, 0, 1, 1. Again, starting with 0 and ending with 1. Next one, you guessed it, 4, 0, 0, 0, and 1, 1, 1, 1. Now, since we already have 8 arguments here, this doesn't necessarily apply, but I just want to, you can maybe test yourself. But what if we had one more input? How would you start writing the zeros and ones for the 4th input? Let's say this one. How would you do it? If you guessed 8 zeros and 8 ones, then you're completely correct. Exactly. But notice that if we did have 4 inputs, then we would have 16 arguments. And that means that all of these other switches would have 16 arguments, right? Okay, but let's focus on the current problem then. Okay, so we don't need the 8 anymore. 8 helped us out. So now we must go to the outputs. This one unfortunately doesn't have a trick like how we have it like how we had it for the inputs. This one you just have to think logically. How do we do it? Well, now we have to think about that when switch number 1 is off and switch number 2 is off and the main switch is off, then all the switches are off. So both of the outputs, so most of the lights, let's actually write this and 1 hertz. Okay, so both of the lights are off in the first scenario. What about the second scenario? So switch number 1 is off, switch number 2 is off, and the main switch is on. So if both of the switches are off and the main switch is on, then both of the outputs are off. Why? If you're confused about how this works, we could have a look you can have a look at the problem again. So the problem is saying that when input 1 is on, then light 0.5 hertz can also be on. And when when switch number 2 is on, then the second light can be on. But it's saying that when input, so the main switch is on, none of the lights can be on. So they are both on state 0. So knowing that, we can already just go and put zeros every single time we see a 1 for the main switch. So 0, 0, 0, 0, and 0, 0. So as long as main switch is 1, none of the inputs can be on, because as long as the main switch is on, it does not care about the state of the other 2 switches. All right, now we have 3 scenarios left. So this scenario is saying that the switch number 1 is off and switch number 2 is on, and the main switch is off, allowing the output to actually be on. Then of course output light at 1 hertz is on because switch number 2 is on, and light 0.5 hertz is off. All right, then another scenario is saying that when the main switch is on, when the switch number 1 is on, switch number 2 is off, and the main switch is off. Of course, it's allowing the outputs to be on, but the first light is on and the second light is off. Great. And finally, we have when both of the switches are on and the main switch is allowing them to be on. So both of them may be on. Okay. So with the truth table, we have kind of spat out all the possible scenarios. So these are all the possible scenarios in all the different combinations. What is really important to us is where we have the output 1, because output 0 is just kind of irrelevant. So I'm going to highlight these rows. Oops, that is terrible. Like that. And the second one. Finally, we have another one. Okay, so great. This was our first truth table, and these are our results. So when switch number 1 is off, switch number 2 is on, and the main switch is allowing the outputs to be on. And so when it's 0, then switch number 2 may be on. When we reverse the situation, when switch number 1 is on and the other switches are off, then light number 1 starts flashing. And finally, when both of the switches are on and the main switch is off, of course, both of the outputs may be on. All right, thank you.